Well, greetings, mathletes, and welcome back. Today we're going to be talking about a particular technique of integration. It's called the substitution method. Sometimes it's called U-substitution. If you say either one of those things, actually, especially if you say U-substitution, people will know that you're talking about an integration technique. In any case, what this technique actually is, if you remember the chain rule from when we were taking derivatives, this is actually that same process, but in reverse, right? So we're undoing the chain rule is what we're doing. And so, um, I could go ahead and write out all the theoretical stuff first and then look at an example. But I think it's going to be a little bit more clear if I do an example first and then we look at the theoretical stuff so we can compare the two. So that's how we're gonna start out here. So without any further trouble here, let's go ahead and get started. Yeah, so let's take a look at our first integral here, and then we'll talk about what it means. Oh, let's make that a little thinner. There we go. Clear that off again. There you go. Let's try this one more time. So we want the integral of 2 times 2x plus 4 to the 5th power dx. Now, any of the antiderivative techniques that we've looked at so far, they're pretty much not going to work here. The only one that would work is if you went ahead and multiplied out this whole thing, 2x plus 4 times 2x plus 4 times 2x plus 4 all the way up to 5 times, get a huge polynomial, and then take the integral term by term, which would work. But it's a lot of work is the problem. And so this is how we go about making our substitution. So we're looking for some kind of a composition is what we're looking for. And I can see that 2x plus 4 is being composed with the function x to the 5th, right? Because I'm raising it to the 5th power. So you're looking at this a lot like the chain rule. You're looking for some kind of a composition. Okay, so our first attempt here, and actually this is going to be the correct attempt, is that u is equal to 2x plus 4. Okay, so what we can do then is once we set that, we can replace 2x plus 4 with u. And so it becomes u to the 5th. But then we still have this problem of the 2 on the outside and the dx, because now I have a u in my integrand, right? So now this is 2 times u to the 5th dx, right? There's our problem, is the dx, because we've just rewritten our function in terms of u. So we need to figure out what a du would look like, because if we're going to integrate this with respect to u, we need what du is. And so this is how we go about finding it. We find du dx, and I can see that that's going to be 2, right? Okay, now, and again, this is one of those places you can actually treat the differential like a fraction. I can just go ahead and move the dx to the other side and say du is equal to 2 dx. Right? So if I can find a 2 dx, I can take that out and replace it with u. Well, I have a 2 and a dx, so I can actually write this. Right? I can separate it out. And that means that's my du. So now I have the integral of u to the 5th du. And that's something we know how to take an antiderivative of because we have the power rule. Right? And remember, because this is an indefinite integral, we'll have to put a plus c on the end of everything because we don't have limits of integration here. There's no integral from a to b or anything like that. So this is going to be u to the 6th over 6th using the power rule plus a constant. And all we have to do now is go back up and look at what u was. And we'll put it back in here. So the final answer here ends up being 2x plus 4 to the 6th power over 6 plus a constant. Right? And so we found the indefinite integral. And if you want to check, right, if you want to check yourself to make sure you did it correctly, take the derivative. You notice you'll have to you use the chain rule, so it's the derivative of the outside times the derivative of the inside, or vice versa, and you end up with your old the old integral back. Because if you take the derivative of 2x plus 4, you get the 2. And if you take the derivative of u to the 6th over 6, you get u to the 5th, which would be this, right? The 2x plus 4 to the 5th. So you do get everything back. You can always check your work by taking a derivative. Okay, so that's our first example. What I want to do right now is take a look at the chain rule itself for derivatives, and then we'll look at how this applies to integrals here. Okay, so if I look at the whole idea for derivatives, right? If I'm taking the derivative of a composition, what I end up with is f prime of g times g prime of x, right? That's what the chain rule tells us. What we're actually doing, because we're working our way backwards here, we're looking for an integral so that I'm seeing a composition of functions in here. And we'll just throw a dx on there, right? So this is the situation I'm looking at. If I take this integral, let me move some of this stuff over so I don't bleed over here. We'll put a plus c here so we know it's there. If I look at the integral I just computed, and I'm going to rewrite the order. This is 2x plus 4 to the 5th times 2 dx, right? That's what we're looking at. So this part right here is f prime of g of x, right? And so what we're looking for is the derivative. This part right here ends up being your du. So g ends up being your u, and g prime is your g prime dx is your du. So where am I here? Yeah, so that's f prime of g times, and then g prime of x dx. So what I did was I said, well, let's let g of x equal u, and so g prime of x, whatever that happens to be, is your du. Oh, I need a dx on the g prime. Let's try that again. G prime of x dx equals your du. And that g prime is really a du dx because g prime is u. So that's actually what we're doing. That's the theoretical side of it. And I know that got a little messy there, but that's what's going on. So we're really trying to construct the whole chain rule backwards. That's the main goal. Now, one of the things you might have noticed is that it was really, really, really convenient that there was a 2 in our problem. There isn't always. So I want to go ahead and take a look at one of these that doesn't have a constant and look at how we deal with that. So let's go ahead and take a look at, let's switch colors again, the integral of 6x plus 1 to the 9th dx. Okay, so it seems like it's suggesting that our u should be 6x plus 1. That seems to be the thing that that looks like what the composition is here. So we're going to try it. So u is equal to 6x plus 1, and that means that du, and I'm going to skip the whole du dx part of this. I'm just going to start writing it so they're already separated, because that's what most people do. The derivative then would be 6, and I need to tack a dx on there. So I need a 6 in here, and I don't have one. So this is how we handle it. Since you are allowed to pull a constant through an integral, what we can do is put the number we need on the inside, right? So I'm just going to put a 6 in here. Right? But I need to multiply on the outside by its reciprocal, right? Because I can always bring this in to make it a 1 again if I wanted to, right? So if I multiply 6 times 1/6, it becomes a 1. I'm back to the original problem. So whatever constant you need to put in, always put the reciprocal of it on the outside of the function, on the outside of the integral. Okay, so now I have a 6 dx, right? There's my 6, there's my dx, and I have a u. So now this is 1/6 the integral of u to the 9th du. Well, the integral of u to the 9th du is u to the 10th over 10, right? Well, we know what u is. It's 6x plus 1. So this ends up being 1/6 times 6x plus 1 to the 10th over 6. Oh, over 10, excuse me. And actually, just looking at this, I can go ahead and put that 6 in here, multiply the 1/6 in. You can't really multiply anything in on the top because it has that exponent, but the bottom doesn't. So this is 6x plus 1 raised to the 10th power over 60 is what this ends up being. And if you go ahead and take the derivative, you'll find that you end up exactly where you started. Oh, and I almost forgot. Actually, that plus C is going to frustrate you guys on the homework because if you leave it off, you're going to get marked wrong. So make sure you're putting that plus C in there. And it is super easy to forget because it's not a computational C. It's one of those things you just it's like remembering to put the period at the end of your sentence kind of a thing. It needs to be there so it represents all of the antiderivatives, right? If we had a definite integral, we wouldn't need the plus C. Okay. So that's the basics of how to get started on this. Now we're going to play with some other stuff now too, because we could have trig functions, we could have square roots, we could have all kinds of stuff. So let's go ahead and look at the next problem here. All right, so let's say I have the integral, what do I have for this one? Of sine squared x times cosine x dx. Okay, now looking at this, I can't think of any integrals off the top of my head because sometimes you can just remember how an integral works. But in this case, I'm not seeing anything that's an obvious integral. So we'll go ahead and take a look at this. Now, I know that cosine is the derivative of sine, and negative sine is the derivative of cosine. So we have a function and its derivative here. If I choose cosine as the u, I do get a negative sine dx, right, for my du. But this is a sine squared. And so that's going to be a little more work, I think. If we go ahead and call u our sine, we'll call it sine x, then du is equal to cosine x dx. And I have one of those. So this is now the integral of u squared to u. So that's simplified quite a bit. It looks nasty, but it's actually quite inexpensive. So that means that this is u to the third over 3 plus a constant. And all we have to do is plug in our u now. So this is now sine cubed x over 3 plus a constant. Right, so that one actually wasn't too bad. It probably looked a little nasty to start with, but I think the hardest thing here is to see the function and its derivative inside of your integrand, because some of it requires you to kind of halfway take a derivative in your head as you're going. So also the other thing I want to warn you about is sometimes your first guess for u isn't correct, and you have to try to do something else. So keep that in mind also as you go through this. It's okay to not have the correct u to start out with. A lot of the time what ends up happening is trying something gives you a little bit of insight on what's going to happen if you choose the other thing. And so you get information by trying something. So don't be afraid to just try something. The worst thing that can happen is it doesn't work, right? That's worst case scenario. That means you have to try something different. So what? Okay, so let's go ahead and take a look at another one here. So let's go ahead and clear this off. And I'm going to start making these a little less obvious, I think. Um, so let's look at 9, what is it we got, r squared? 9r squared over the square root of 1 plus r to the third dr. Okay, now, so let's see what we can get out of this. What do we want for our u? Now, I'm noticing something. I see an r to the third down here in the denominator, right? And I know if I take the derivative of an r to the third, there's an r squared in that expression, right? And I have an r squared in the numerator. So that tells me I'm probably going to use the radicand down here in the denominator as my u, right? When you have a constant, like a 1, those go away when you take a derivative. So include those with your u. Oops, I actually wrote the problem wrong. Hang on. That's supposed to be a minus. I don't want to change everything. So u is 1 minus r cubed. And so du, well, the derivative of 1 is 0. If I take the derivative of negative r cubed, I get negative 3r squared dr. Okay, so let's see what we can do with this now. So let's let's see, we're going to have to manipulate this. So I think the denominator is probably pretty straightforward. That's going to give me the square root of u. Okay, I can deal with the square root of u. Now our dr. Now I want to point something out here. I have 9r squared. What I need is a negative 3r squared. Notice that if I have negative 3 times negative 3, that gives me a 9 also. Now, there's more than one way to handle these constants on the outside. But so this is one of the ways you can deal with this. I can put a negative 3 on the outside and then put the rest of this negative 3r squared dr back in here. So you notice if I multiply the negative 3 in, that gives me the 9 again. So nothing's really changed other than the way it looks. So another way to handle this, and I'm just going to step to the side for a second, is to just pull the whole 9 out and look at it this way, right? And then put a negative 1/3 on, or excuse me, a negative 1/3 on the outside and a negative 3 on the inside, right? So that way, if I multiply those in, I still get my 9 back. And notice too, if I multiply negative 1/3 times 9, it gives me this negative 3 back, right? So there's more than one way to get to it. So it's just a matter of however you see it. 9 factors into 3 times 3, so it works out well. So now, negative 3r squared dr works out for us. And it's because the negative 3r squared is in the numerator. If it was in the denominator, we couldn't do this. So now we have, we've transformed this thing into the integral of du over the square root of u. Now I can look at this as 1 over the square root of u if I want. Yeah, there we go. Okay. Yeah, and actually it's probably easier to look at it this way. Right? And if I look at it that way, that tells me exactly how to deal with this integral. This will be negative 3, that's for the outside. And then the integral of this is u to the negative, oh, excuse me, 2/3. It'll be negative 2/3 u to the negative 3/2. Right? So we can cancel that out. The negative cancels and the 3 cancels. And I end up with, and then I'll go ahead and substitute back in for the u. That's 1 minus r cubed. This ends up being 2 times 1 minus r cubed to the negative 3/2 power plus a constant. Now, you could go back through and rewrite this in terms of roots and stuff. There's no reason to, right? There's nothing wrong with using a negative exponent. There's nothing wrong with using a fractional exponent. And there's no reason that we have to convert this back to a root in this case, because we're not using it for anything right now. If we're using it for something, well then yeah, we're going to change it into the form that's easiest to use. But we're not using it for anything. So this is perfectly good. This is absolutely perfect the way it is. You just can't forget your plus C. Okay, so note again, this was a little weird how we had to handle that constant, right? We had to break it up so that it came out nice and we could get the number we wanted on the inside. Okay, so let's take a look at another one here. All right, so let's suppose we have x times x minus 1 to the 10th power dx, right? And we're trying to find this indefinite integral. Well, the way you typically want to start is, you look for a composition. I can see x minus 1 is composed with x to the 10th, so let's go ahead and take a look at that. Let's try that first. So u is equal to x minus 1, so that means du is equal to 1 dx, or just dx, and that leaves my x over here on the side by itself. So I can swap this out, but I have a little problem here. I still have an x in there. So what's nice, especially when it's something it's basically linear, it's basically the equation of a line, that means you can solve for the other variable. If u is equal to x minus 1, then if I add 1 to both sides, then 1 plus u, or actually let's write it the other direction because it's nicer to look at, u plus 1 is equal to x, right? So that means I can substitute u plus 1 in for x. So now this turns into u plus 1 times u to the 10th dx. Okay, now I can switch that to a du because dx is equal to du. Now, it might look a little funky at first, but if you distribute the u to the 10th at this point, you end up with this: u to the 11th plus u to the 10th du. And we can take integrals of both of these things pretty readily. So if I take that integral, that is equal to u to the 12th over 12 plus u to the 11th over 11 plus c. Well, all we have to do is plug this back in for u now. So now this is x minus 1 to the 12th over 12 plus x minus 1 to the 11th over 11. And I don't think it's super obvious to do this, right? To go ahead and solve it for x. But that's another really good trick. Once you decide what u is, if you can't substitute everything out, then solve for x and substitute whatever the expression in terms of u, substitute that in for your x values. And that actually it simplifies a lot of things, as you can see. It just turned this nasty looking thing that didn't seem to have any traction into just kind of a standard integral. Okay, so I think that one is a little less obvious, and it's this trick that makes it less obvious. Okay, so let's take a look at another one here. Let's go ahead and clear this off. And this is another one I think is less obvious as well. Really, it's just a matter of getting a hold of whatever u is. But sometimes that's a little funky. Times cosine to the 3rd x dx. And the only reason I put the parentheses was so that you could tell it was not inside the square root with the sign. Okay. So again, we're in this position. We know that cosine is the derivative of sine, and negative sine is the derivative of cosine. But we have a problem. If I make sine, oh, that got smaller. Hang on. Must have bumped something. Try one more time. There we go. This is frustrating. There. Okay, now we have the correct thickness. If we let u equal sine x, right, we have this problem. Du is cosine x dx, but if I make that substitution, I have a cube in there, and that's a problem, right? I can't have a du cubed. I need a du just sitting out there by itself. So we have to get creative here. I want to point out cosine cubed is cosine squared times cosine. So let's start there. And a lot of this will go quicker than what you're going to see on the screen here. I'm just explaining every step and why. So a lot of these things, once you get a handle on it, you'll be doing in your head. Let's look at it this way, as cosine squared x times cosine x dx, right? So this is my du, right? I got that part. I have to do something with this cosine squared because u is sine. So I have to get rid of everything that has an x in it. But remember that cosine squared x is equal to 1 minus sine squared x. So this is where our trig identities come in. So we're going to rewrite this whole thing now. And I'm going to write this as sine to the 1/2 power times 1 minus sine squared x, and then it's times cosine x dx. So now I think we can make all of our substitutions. I have my du here. I have u, and then sine x is u. So let's take a look now. So this is now u to the 1/2 times 1 minus u squared du. Well, at this point, I'm just going to distribute, right? If I distribute this, I'll be able to just take the integral term by term. So this is now the integral of u to the 1/2 minus, and since we're going to be adding exponents, that's going to make it 5/2, u to the 5/2 du, right? And so now I can just take it term by term. So the integral of u to the 1/2 is, u to the 3/2, 2/3 u to the 3/2 minus, and then here it's going to be 2/7 because we're going to add 1 to 5/2. So we'll have 2/7 u to the 7/2 plus a constant. And all we have to do is put in our sine x again. So this is now 2 sine to the 3/2 x over 3, or you can write 2/3 sine to the 3/2, either way, minus 2 sine to the 7/2 x over 3, and then plus a constant, right? But that one was a little bit tricky because we had to split up the cosine in a creative way to try to get the things we want. And that's usually the biggest trouble with this. If they're set up nice, so you have a du and a du, no problem. It's a straightforward process. But when you have to hunt and twist things and reorder them so that they look like something you can use, that's where the trick comes in. And that's what really ends up taking some experience. Okay, so I want to look at one more here. And let's see. Okay, so last example here. Let's go ahead and take a look at the integral. Where did I put it? Their cosine of 1 over t minus 1 over t squared dt. Okay. So looking at this, there's a few things you might think about. Well, what if u is t squared, right? So that would make du equal to 2t dt, right? And well, that's a problem because I have no way of getting this t out of the cosine. So that means we can't use that. So let's try something else. Now, I think it's pretty clear that this 1 over t minus 1 is composed with cosine, right? There's a composition there. So maybe we can try that. Okay, and if I take the derivative of 1 over t minus 1 with respect to t, I get negative 1 over t squared dt. Okay, well, that's convenient because if you hadn't noticed, I can actually pull this t squared out as a 1 over t squared. Right? I can look at this function this way. And you notice a lot of these, it comes down to looking at them a different way, right? And so you have to be able to let your mind reorganize these problems so that you can look at it from a different point of view. Okay, so we have that, but we have a problem. That's supposed to be a negative, and this is positive. So what we're going to do is just put the negative in. As long as we put one on the outside too, they'll cancel out, and we still have the same thing. Okay, so it looks like now I have everything. So, okay, let's do this. So now this is the integral of, let's see, that would be cosine u, and then negative 1 over t squared dt is my du. So we've actually simplified this quite a bit. So let's see, we know that the integral of cosine is sine. So this is going to be negative sine u plus a constant. And we know what u is, so this is now negative sine of 1 over t minus 1 plus a constant. Now you notice I was able to get through quite a few examples here, as far as what compared to what I normally do, and it really hasn't been very much time. We're a little over 30 minutes right now on the recording. These do tend to go quickly, but only if you see it. If you don't see it, you often spin your wheels on these trying to see what the right thing is. And sometimes you have to guess, and it's okay to guess, and it's okay to be wrong. Learn from what was wrong. When you go to check an answer, when you go to check your u, let me do this. When you go to check your u to see if it's going to work, there's things you can learn if it doesn't work. And those things you learn often direct you to what you should be doing. So pay attention to your mistakes as well. I think they're very important to pay attention to your mistakes in this too, because you're going to learn a lot from doing the wrong thing. And unfortunately, with this type of thing, you tend to do the wrong thing a lot when you're first getting used to it. So have some patience with yourself. Get through these things. And if you need help, please come and see me. I'm usually sitting here just waiting to help people. So in any case, that will end our lecture for today. And so until next time, keep your pencils and your wits sharp.